But let's look at the magnetic moment. Because that's something we need for NMR shieldings. And by the way, maybe I should say one thing before. When I talked about that magnetizability, there will be two contributions. There will be a contribution from this operator twice, and there will be a contribution from this operator. And this one gives rise to the contribution which is called the diamagnetic contribution, whereas this gives rise to the contribution which is called the paramagnetic contribution. But back to the magnetic moment. The story is sort of very much the same. Let's look first at the linear term. Again, and that operator is called PSO, and PSO stands for paramagnetic spin orbit. And I left spaces because, although it's not included in the name, this is nuclear spin electronic orbit. Because there is also a spin orbit operator, but that's electron spin with electron angular momentum. That's the spin orbit coupling that we have. We have a heavier element that the electron spin and the electron angular momentum couple to the total momentum of an electron. But this is nuclear spin and the coupling between the nuclear spin and an electronic orbit. So if I insert now my expression into, where is it? Up there, A dot P. Then, and I do again, like we did for here, instead of A dot P, I rather want to write it immediately where I switched the cross product and the scalar product. And if I do that, then I get E divided by ME, like before. That's the, from up there, E divided by ME, then I get a sum over all electrons. The vector potential here for nuclear has mu 0 divided by 4 pi. And that mu is actually, that's the analog, the magnetic analog to that epsilon 0. Right, then I have Ri minus Ra vector divided by Ri minus Ra to a third power. And it should have been cross Ma, the magnetic moment of the nucleus, and the dot product with P, but I immediately switch them around, so I get cross P I and dot the magnetic moment of the nucleus. And here, I mean, here there's no danger. I mean, I don't have to be worried about that. I have a gradient operator now standing there and the magnetic moment of the nucleus afterward. Because this is the gradient acting on electronic coordinates, and the magnetic moment of the nucleus has nothing to do with electronic coordinates. So here I can, without any problem, use the normal cyclic permutations which I had up there. So going from this, I went immediately to that. Now, remember, the nuclear magnetic moment is just another way of writing. It's related to the spin, where you have the nuclear G factor the nuclear magneton, which is sort of units divided by h bar, and then I could also write it with the nuclear spin. Here, vector or operator. So here I have nuclear spin. So that's the part, the nuclear spin part, that's this one. That's in the M. And where's the electronic orbit? Well, this here. That's R cross P again. So I can also write this as E ME mu 0 divided by 4 pi sum over I, and then I can write it as L I vector operator, but now with respect to the position of the nucleus, not with respect to this rather arbitrary gauge origin as I had here. But now it's a particular origin, it's the origin of the position vector of the nucleus which I have here. So that's the angular momentum, and then it's divided by Ri minus Ra to the third and times Ma. Just keep the Ma here. Like this. Well, this is actually the angular momentum of the electron. I mean, if I talk about angular momentum, I always have to have, I mean, this is rotation. It's circular movement. And I always have to sort of define circular movement around what, or with respect to what. That's where the angular momentum. So here it's the movement around that nucleus. So that's the what is called the PSO, paramagnetic spin orbit operator. The interaction between the motion of the electrons with a nuclear magnetic moment. And that operator will pop up every time you have an interaction between electrons and nuclear magnetic moments. So you're going to have that in NMR, because the shielding constant, which is the constant behind the chemical shift, that is an external magnetic field and a nuclear magnetic moment. So you will have an interaction of the nuclear magnetic moment with the motion of the electrons. You will also have that obviously in the spin-spin coupling constants, because how does the nucleus with its spin tell the electrons what is the direction of the spin? That is through this interaction. Nuclear spin via its magnetic moment interacting with the angular momentum of the electrons. And I mean, angular momentum of something which has a charge means magnetic moment. So this is a magnetic moment interaction term. You also have the same in ESR spectroscopy, where you look at the electronic spin states, but they are perturbed by the nuclear spins also. That's splitting of the lines in the ESR. There you have is precisely the same interaction. You have a magnetic moment of the nuclei interacting with the motion of the electrons. I mean, you can write that, I think Frank does, you can write that then as sort of a PSO operator. Let's call that P. PSO operator of nucleus A times, and then the magnetic moment and a sum over all nuclei. Because in the other case we had a magnetic moment, so here we can define sort of a paramagnetic spin orbit operator, which is all that.